All right, hello. Today we're going to talk about populations and specifically the dynamics that occur in the populations of these organisms. So let's get started. Before we begin talking about populations and their dynamics, I thought we'd start off talking about the differences between generalist and specialist species. So generalist species are species that can live in a variety of locations. They can eat a variety of food sources, and they tend to have very broad niches. Compare that to a specialist species. These are organisms that require specific places to live. They have very narrow niches. They don't eat a wide variety of foods, kind of like my kids. But if you look at the two pictures below, you'll see the raccoon is a very, very classic generalist species. It can eat anything. It can really live in a lot of places. And I pretty much see them in my backyard every single night trying to find whatever they can to eat. A panda, on the other hand, very specialized, right? We all know they live only in certain forests of China. They only eat bamboo, and so thus they are characterized as a specialist species. All right, so look at their habitats, right? Because this will give us some information about how their populations work. A specialist species habitat, they tend to be in very constant habitats. They can't have a lot of change because they're not adapted to that change. So they really do succeed in areas where they have very little environmental change. A generalist species, they can endure the change. And so if their population is subjected to some sort of changing environment, they tend to succeed. And that leads to an increased number in their population. So now let's look at some of their reproductive strategies. So if you're a population, how do you reproduce in order to survive? Because that's ultimately the main goal, right? The end game. How do you survive? So there's two different categories of reproductive strategies. We have R-selected and K-selected. You might also see them called R-strategists or K-strategists. It's the same thing. But if you're an R-selected species, you tend to have all of these characteristics listed below. So you have many small offspring. You don't really take care of your offspring. You may have them and then like 6 weeks later you leave. Unfortunately, a lot of the offspring pass away before they reach the reproductive age. They have very high population growth rates because they tend to have a lot of births. And these tend to be the generalist species. K, on the other hand, is quite the opposite. So K-selected species, they tend to have fewer and larger offspring. They don't necessarily leave their offspring once they're born, so they tend to stay with them. Like for humans, I think it's expected that you stay with your parents until 18 years of age. Most of the offspring will reach their reproductive age. They tend to have a lower growth rate because they don't have as many births, and these tend to be the specialist species. So these are just the two general categories. Of course, you're going to find species that fall in between, but most of the time it's either one or the other. The way I like to remember it, R stands for roaches or rabbits. Just think of it that way. Because roaches and rabbits, they tend to have a lot of offspring. They don't care, they don't take care of their offspring. K, on the other hand, I like to think of them as the killers because they are oftentimes like the predators, right? The predators, the larger organisms, they only have a few babies at a time. They really take care of them to make sure that they reach their reproductive age. So I'm going to go through a couple of examples here, and I want you to think about, are these R or K selected species? So our first picture here, we have our lovely bunny rabbits. So I hope you're thinking to yourself, yes, this is an R-selected species. Next, we have our tortoises. So just by looking at the picture here, you can see they've laid an abundant number of eggs, way more than the 1, 2, or 3 that a K-selected species will lay or have. So these are classified as R-selected species. Okay, our killer whales are orcas. These populations, they are case selected. They have very few offspring. They take care of their offspring, and hopefully most will reach their reproductive age. And our manatees of Florida, these are also case selected. All right, so just take a moment and think about why, if you were an organism, why would it be good to be an R-selected species? What are the advantages? And if you're a K-selected species, what are some advantages of being a K-selected species? And then just think about to yourself, what would you rather be? Would you rather be R or K? All right, well, our selected species, they tend to grow exponentially. So if you take a look here, I'm sure you're familiar with exponential growth from your math class, but basically it's doubling over time. So as time progresses, the population size increases. This is common until the organism runs out of food. And then what you're going to see is the population will crash, and then it grows exponentially again, and then it crashes, and then it grows again. That is just how they've adapted, and apparently it seems to work for those species. Something that you may also see with exponential growth is something called biotic potential. And biotic potential is really the maximum rate at which a population can reproduce if they have ideal conditions. What do I mean by that? So ideal conditions are things like unlimited food sources, unlimited shelter, unlimited water. All of those things will lead a population to grow exponentially to reach its biotic potential. Compare that with logistic growth. So most case-selected species will grow logistically. So they do start off growing, right, like you see with exponential growth, but then over time they reach a level and they stabilize. That stable level is called its carrying capacity, and it's pretty much the number of individuals that an environment can hold where that population remains healthy. If it goes over the number, so if the population exceeds its carrying capacity, the environment will usually do something to regulate to put the numbers back down to its carrying capacity. So again, you can always find the carrying capacity of a population if you graph their numbers and you just look for where it levels off or where it stabilizes. Draw a line to the y-axis and you can see the number of individuals. You may get asked this on an AP test or some sort of multiple choice question test. It tends to come up a lot. So again, a carrying capacity is pretty much the maximum number of a population that an environment can hold healthfully. Now, I also want you to remember that a carrying capacity is not the same throughout the year. It can definitely change. So first, like just think of, I don't know, grasshoppers, right? Maybe in the summer, there's tons of vegetation and the grasshoppers can thrive and grow. However, when it gets to the winter and there's not as much vegetation, the grasshopper's carrying capacity may not be the same because the environment cannot hold the same number of grasshoppers healthfully as it once did in the summer season. So keep in mind the carrying capacity is dynamic. It is not stable. It will change throughout the year. All right, so this is just general trends and rules that you see with populations. So when resources decline in an environment, so when they become limited, number one, you start seeing an increased mortality rate with the organisms. Number two, you see a decrease in the fecundity, so the amount of babies being born gets reduced. And this all leads to a shrinking of the population, and sometimes that population does go under its carrying capacity. By the way, carrying capacity is usually always represented with an uppercase K when you're talking about logistic growth. Invasive species are interesting in that most of them tend to be R-selected. So again, here is our infamous cane toad. We talked about them in the last lecture. They are an invasive species from Australia. Now, they, like other invasive species, tend to be R-selected in that they have incredible numbers of offspring. For example, the cane toads in Australia, they lay something like 20 to 30,000 eggs in just one city, and they can reproduce up to 3 times each year. They also don't really take care of their offspring, and if they were in their native area of Central America, many of those eggs wouldn't reach reproductive age. However, since there are no natural predators of the cane toads in Australia, a lot of them are reaching their reproductive age and having even more cane toads, which leads to more of a problem. So invasive species, they tend to be R-selected. The last thing that we need to cover in population dynamics is survivorship. So survivorship is a measure or proportion of how many organisms in that population survive to breeding age. So again, that all changes with what species or what population you're talking about. There's 3 different categories. There's type 1, type 2, and type 3. Type 1 survivorship tends to be the late losers. So that means you have organisms in that population, and a lot of them do make it to old age, and then that's where you start seeing the late loss in life. So those tend to be the K-selected species. Type 2, those are just the constant loss. So as you go through their lifespan, you get a gradual loss of the population. Those can be in between, they're kind of like the in-betweeners. And then we have our type 3, which are our early loss species. So that means you may have a lot of organisms born in the population at one time, but they do not make it to reproductive age. Those tend to be the R strategists. You can illustrate survivor with the generalized survivorship curve. So you have your type 1, which are your late loss organisms or your populations. So you have them, obviously they're young when they're born, and a lot of them do survive, and then they die off when they get old. Type 2 are the constant loss populations, and then type 3 are the early loss populations. So you have a lot of organisms at the beginning, and then they don't quite make it to reproductive age. All right, and this is an image taken from the AP Environmental Science textbook. You can see rhinos are a classic example of the type 1 survivorship curve. Birds are constant loss, so those are type 2, and type 3 would be really many of the smaller fish species. When looking at how big a population can get, you need to look at things that are called density independent and density dependent factors. So for example, a density independent factor is something that will regulate the population's growth rate. Okay, so how fast it's growing, but it really has nothing to do with their density or how much land they have. For example, major storms are good examples of a density independent factor. If you're in an area and a hurricane comes through, it's going to wipe out some populations that are in the area. It really doesn't matter how dense that population is or on how much land that population is. It's going to affect the population's growth based just upon the force of the storm. Compare that to density dependent factors. These are things that can regulate a population size based upon how dense the population is, right? So density is a measure of how big the population is over its area size. So the less land that you have, okay, the more pressure is going to be put on those populations. A great density dependent factor is disease. Okay, disease definitely can control a population's growth rate, right? But the more dense that population is, the more likely it is that disease will spread because the population is crowded. The population may be big in a small area of land. So that makes it really easy for the virus, for example, to spread through the population. So those are just some things that can control population growth rates.